In Chapter 4, we're going to study force system resultants, but the main concept is moments. And this is a new concept for many of you. The basic concept of moments is that they turn things. You also need to remember that moments are vectors. So a vector has a magnitude and a direction. The magnitude of a moment is a force times a perpendicular distance. Again, the magnitude of the moment is the force times the perpendicular distance to a point. You have vectors, perpendicular, multiplying. That all implies cross product. That means we're going to have to use the cross product that we learned earlier. Here's the concept of a moment. The most basic concept of a moment is a force times a perpendicular distance. Here we have the force on the end of this adjustable crescent wrench, and here is a distance, and the key thing is that this distance is the perpendicular distance from the force to the point in question. The total moment of that force will be the force times the perpendicular distance. I said it was a vector, and so the vector has a direction. In this case, it'll be counterclockwise. Okay, if you are pushing or pulling on a wrench, you're doing it wrong. You know that to turn a nut or to turn a bolt, to use a wrench, you push perpendicular to the distance, and this is because you're trying to put a moment on that bolt or nut. Again, it's a force times a perpendicular distance. In this case here, if you are pushing or pulling along this line, there is no perpendicular distance, and no matter how hard you push or pull, that will never turn the nut. You know this intuitively. To maximize your moment, you need to have a perpendicular force to the distance. There are fundamentally two kinds of moment. There's bending and twisting. Here you see there's a force here, and it's causing this diving board to bend. This would be the perpendicular distance here to the point where it's bending. Here you have a torque. You are twisting this screwdriver, and you can think of it as putting a force this way and maybe a force this way that are both in 3D this perpendicular distance away from the axis of the screwdriver. This is called torque, and this is called bending. But they are both force times distance, and they are both moments. The bulk of what we're going to do are two-dimensional problems. Let's talk about two-dimensional moments. What it will involve is a scalar calculation of force times the perpendicular distance. You'll have to do some geometry to get the perpendicular distance. And then a direction, either clockwise or counterclockwise. We'll explain this in a little bit. The magnitude is the force times the perpendicular distance, or you can get the perpendicular force, the component of the force perpendicular to a given distance. They're the same thing. Force times perpendicular distance, or perpendicular force times a distance. As for the direction, any two vectors make up a plane. So in a 2D problem, you'll have, let's say, the distance r to the force, and then you'll have a force F. These two vectors I've drawn on the surface of my iPad, and that's the plane, the surface of my iPad. And if you do r cross F, remember the cross product is always perpendicular to the two vectors. So if these two vectors are on the surface of my iPad, r cross F will be perpendicular to the surface of my iPad it will be either pointing up out of the iPad or into the surface of the iPad. The direction is therefore up or down, so we can think of it as counterclockwise using the right hand rule, that's up out of the paper, or clockwise using the right hand rule, that's down into the paper. This is counterclockwise or up. This is clockwise or down. Here's an example from your textbook that I want to look at in a little bit more detail. We'll go through all these forces and get their moment about the origin by examining the force and the perpendicular distance. So here is a 50 Newton force, and its perpendicular distance from the origin is 2 meters. We have force of 50, distance of 2, so a moment of 100, and it's going counterclockwise around the origin, so it has a negative. Next, we have this 60 newtons. Its perpendicular distance to the origin is 0. It goes right through the origin. It has no offset. It has no perpendicular offset. The force is 60. The perpendicular distance is 0. It has no moment. That's just like the picture I drew where instead of trying to put a torque or a moment with the wrench, you're pushing and pulling the moment right through the nut. It'll have no moment. It won't work. Finally, we have this 20 Newton force here. Its perpendicular distance to O is this distance right here, right? That's perpendicular to O. Doing a geometry, it's 3 times sine 30 degrees. Here, this distance right here is 3, and so this distance here is 3 times sine 30 degrees. There you go. Here's the force. So the moment is 20 times 3 times sine of 30, which happens to be 30. And it is going counterclockwise around the origin, so it is positive. Then we have this 40 newtons. Its perpendicular distance to O is this. That's the distance perpendicular to the 40 to this origin O. This distance here is 3 cosine 30 degrees, and this distance here is 4 meters. The total then is 4 plus 3 cosine 30 degrees. The force is 40, and when you multiply it all out, you get 263.9. It's going clockwise about O, negative. And you add them all up, and you get minus 334 clockwise. And the units are newtons times meter, Newton meter. This is a typical strategy for getting moments in 2 dimensions. You get the force, you find the perpendicular distance from the point you're interested in to the force, you multiply them, and then you determine if it's going counterclockwise around that point or clockwise around the point, and that will be plus or minus. But what about 3-dimensional problems? For 3D moments, you have to use cross products. And you're going to do R cross F, which remember is not the same as F cross R. What you want to do is find the moment of a force, F, about a point, O. Here's what you do. You draw a dotted line through F. You can either draw this on the paper literally or just draw it in your mind's eye. This is called the force line or the F line. The next step is create any vector from point O to the dotted line. It can be to any point on the dotted line in step 2. It doesn't have to be to where the force is applied. Just pick something that's convenient. If you choose carefully here, you can save yourself a lot of work. This vector from the point O to anywhere on the dotted F line is called the vector R. If it's convenient, Just pick an R that's perpendicular to F and it'll save you some time. Then you do the cross product, R cross F. Let's talk about this F line. Okay, so here we have Katniss about to shoot an arrow. I think of that as a vector. If this is your force vector, the trajectory of that arrow, assuming it doesn't arc up or down, this straight line here, is called the F line. I think the book says something like the concept of transmissibility. I just like to think of this picture. Think of somebody shooting an arrow, and if you go along that arrow forwards and backwards, you just either draw that in or you imagine it with your eyes. That's called the F line. Any point O, you then take a vector from there to anywhere on the F line. It doesn't matter. Okay? You just take the vector from O to anywhere on the F line. That will be R. And R cross F will be the moment, no matter which one of these you choose for R. Why does this work? Why can you pick any distance? The reason you can do that, remember the magnitude of the moment is the perpendicular distance from the force to the point. All these vectors, as long as they start at O and end at the F line, they have the same perpendicular component. They have the same height away from that line F. This concept that you can slide that force anywhere along this line of action, that's why I like to think of it as an arrow being shot, because that arrow goes along a path, and I'm imagining a straight line path. That arrow will be anywhere on that line. That's called the principle of transmissibility. It doesn't matter for statics where you put that force as long as it's on that line that the arrow is being shot. A lot of times before I do this cross product, I imagine the general answer before I do it. You can know the direction of the moment just by using the right-hand rule. In this case, we want to know the moment of F around O. Can you see that force, if you curl your hand around O, it's going to go like this, right? It's going to go counterclockwise around that point O. You're going to have this. You can use the right-hand rule to get the direction of the moment. What I do is I just look at it and I imagine which way is F spinning around O. Some people that's hard to imagine. We'll go over this in class. This is better done in a live demonstration. We've gone over the cross product earlier in the semester. You're just going to have to go back and look at that notes. But to calculate the moment in 3D, you do this determinant. You put ijk in the first row. This is important. You have to put r, x, ry, and rz in the second row, and then f, x, y, and z in the third row. You cannot switch r and f. It's r cross f, not f cross r. You take that determinant, and you'll get this moment vector here. Let's look a little closer. Here it is, written all out, equation 4-8. And we have an R component and an F component in every term there. I want you to notice that there's a RY, an FZ times an X unit vector. RZ times FY times an X unit vector. There's always one of each. Look at this. X, Z, Y. Z, X, Y, X, Y, Z, Y, X, Z. There's always two, an RY and an FZ, and an RZ and an FY. RX, FZ, and you swap it, RZ and FX. And finally, RX, FY, and RY, FX. And there's a plus and a minus. If the order is positive, meaning X, Y, Z, or yzx or zxy. Think of x as 1, y as 2, z as 3. As long as you're going this way in order, 1 to 2, 2 to 3, 3 to 1, it's going to be positive. So look, yzx is going y to z, z to x, it's positive. But if you go zyx, that's backwards, and that's why you get negative. This suggests that we can break both r and f into x, y, z to make our life easier. It's a lot of times easier to do the moment by looking at the components, the x component, y component, z component of r, the x, y, z components of f. From doing these problems a bunch of times in my life, even though this is for 3D problems, I find this also useful for 2D problems. Sometimes getting the perpendicular distance, so you're given f, and you've got this weird r, and you're trying to figure out that distance there, r perpendicular. It's not the easiest geometry problem in the world. What you can do is if you look at just the x and y terms right here, so rx, fy, ry, fx, you get this. The moment is rx, fy, ry times fx counterclockwise positive. It might be easier than doing the geometry. So what I do often is I'll just break the r into the x and y components. I'll break the f into x and y components, and then just do this calculation. You break them into the components, get the moments, force times distance, and make sure you use the right-hand rule to get plus or minus, counterclockwise plus, clockwise negative. Here's a simple example. We want to get the moment produced by the force F about point O. We need a vector anywhere from O to the line that the force is acting on. We could take this as R because it's getting to where the rope is tied to the tractor, or we could use this as R. It doesn't matter. In this case, we're going to use RA, I believe. We could also use RB if we want. It doesn't matter. We'll get the same moment. RA cross F will equal RB cross F, as long as a point goes from O to anywhere on that arrow line. We need the vector for F, so the force is 2 kilonewtons, and the unit vector from A to B is, the vector from A to B is 4I plus 12J minus 12K divided by the length, 4 squared plus 12 squared plus 12 squared square root, and you get this for the force vector. Well, you do RA cross F, let you follow the math, and you get this answer. Oh, here they do both of them. You do RB cross F, you get this answer. Hopefully they're the same, and yes, they are. That's all you do. Let's look at another example. In this example, we want to get the total moment from force F1 and F2 about O. All we need to do is get the moment of F1 about O and add it to the moment of F2 about O. Remember, you pick any vector from O to the line of action. We're going to take this vector from O to A to get the moment of F1 about O. And we're going to take this vector from O to B to get the moment of F2 about O. Here's the vector RA, and there's the vector RB. We need to get the forces as vectors. Thankfully, they're given. You don't have to do any unit vector stuff. And here you have RA cross F1, RB cross F2, and you can do the math, and it comes out to this. The one thing I do want to point out about this example is how do you interpret the answer? Here's the moment. It's some weird vector, 30 in the X, minus 40 in the J, and 60 in the K. Right here, This is the vector drawn, 30x minus 40j plus 60k. This moment, remember, the moment causes things to spin. If you use the right hand rule, stick your thumb along that red arrow and see how your fingers curl around that. They curl this way. That's the 3D moment about O. Think of it as a screwdriver. Your thumb pointing is the tip of the screwdriver, and your hand is turning the screwdriver in the direction of your fingers. That's the moment. And the last concept before we do some examples is that you can get a resultant moment just like you have resultant forces. Remember, we added all the forces and we said that's the force resultant. Well, you just add all the moment vectors and that's called the moment resultant. Both are vectors. There's the force vectors and the moment vectors. In math, the resultant moment is just the sum of all the moments, which is just the sum of all the R cross F's. And in the book, bold means moment. They don't actually draw the arrows there. That's the last concept. What we really need to do is practice. We'll do a bunch of examples.